Hello everybody and welcome to this EB training workshop on physical modeling products. My name is Álvaro de Pascual and I am developer of the multi-year products in the EBMFC. In this practical session we are using EB physical modeling products to visualize the coastal upwelling processes in the Northwest African coast. The EB domain covers the North Atlantic eastern coast, therefore it covers one of the world's biggest eastern coast upwelling ecosystem, the system known as the Canary Current Upwelling System. In the present exercise we are going to learn how to visualize the maps of SST from the analysis and the reanalysis modeling systems. We will compare the results of both products to see the different features of each system. We will learn to plot time series of SST in specific locations, and at the very end of this tutorial we will learn how to visualize vertical sections of temperature to show an example of how the EB products can be used to analyze the vertical structure of the upwelling. This example is written in a Jupyter notebook that runs in a server, so that you don't need to install anything. You just have to use your web browser to access a web page. First of all, on this web page you will see some general notes with instructions to run each code cell. To execute a code cell we just have to select the cell and then press this triangle button at the top of the page. Additionally, there is a shortcut to run the cells using the Shift-Enter keys. This example is written in Python 3 code, and the code cells are these gray cells. To run a cell, you just have to click on the cell, select the cell, and then you push this button here. And when the cell has already run, here appears a number that is the number of the order sent to the server. After these general notes, we have the table of contents with the different sections we are covering with this example. First of all, we have an introduction where we give a short explanation of the upwelling processes. And after that, we put our hands on with sections dedicated to produce different visualization of the upwelling with IB products. Section 2 is dedicated to produce modeling map of SST from the IB reanalysis. Section 3 is quite similar to the previous one, but it is dedicated to produce maps of SST in daily basis from the IB reanalysis system. In section 4, we will learn to plot time series of SST in a specific location, and we will finish this tutorial in section 5, where we will learn to plot vertical sections of temperature. Well, let's jump into the introduction. The coastal upwelling processes occur in coasts where the wind blows parallel to the shore and the induced Ekman transport deflects the surface waters towards the open ocean. Then the mass balance forces the ascending of intermediate waters that are typically denser, cooler and richer in nutrients. Therefore, we can use any variable related with density, temperature and nutrient concentrations to analyze the upwelling. Particularly in this example, we are using a classic variable for upwelling visualization, which is the temperature. In this example, we are using products from EB physical modeling products. However, since there is two different systems that can be used to visualize the upwelling, we will use both, and then we will compare the results obtained here. Here you have the links to the two systems we will use. The physical reanalysis system is focused in providing the best estimations for long time periods. On the contrary, the analysis products are focused in providing high-resolution estimates of the ocean routinely updated. However, in this case, the temporal coverage of this product is not as long as in the case of the reanalysis product. As I said before, in this example we are using the variable temperature that in the EV physical product has the name ZAO. This is a 3D variable, however sometimes in this tutorial we will refer to the surface temperature as SST. This is actually the first level of the ZAO variable. As usually happens in Python 3D programs, the first lines are devoted to load the necessary libraries that are used in the program. So the first code cell we have two in the sample. In this is just a list of the libraries used. Here you have a short explanation of the libraries used and as well as the links to the reference pages. To run this cell, you just have to click on the cell and push the run button. With this, we can put our hands on with the first exercise of this tutorial, the visualization of the upwelling in moldy bases with EV real products. In this exercise, we have a first section where we define the dataset we are using. You can download this dataset from the Copernicus catalog using this information. This is all the information you need to download this dataset. However, we won't spend time on this now. We have already downloaded these datasets in this tutorial, but we encourage you to try to download these datasets. Here in the left panel you will see a file browser with three different folders. In the folder called data, there is two netcdf files, and these two files are the two datasets we are using in this tutorial. The dataset corresponding to the temperature reanalysis in moldy bases and the dataset corresponding to the temperature analysis in daily basis. Well, we start with the program to visualize the maps of SST. The first cell we have is just a cell with configuration options. In this cell we just define some parameters that will be needed in the rest of the program. Here you can find different parameters of the file name of the dataset we are using. As you can see, it is stored in the directory data, and this is the file of temperature reanalysis in moldy bases. We also have the parameter of the variable name, the parameters related with the boundaries of the window we want to plot in the maps. We have the range of dates we will to plot in our maps. These dates has to be defined as date time objects in Python 3. And finally we have a path out. This is a path where we will store the results of this program. As you can see, it is in a folder called results, which is this one in the file browser. And inside the results there is another folder called EV reanalysis moldy. This is the folder where the results will be stored. Now it's empty, but later will have the files resulting of the program. We run this cell, pushing the run button, and we jump to the next cell. It's a pretty simple cell where we just open the dataset file with this line. To do that, we use the library xarray, and we use this function in the library to open the file called fname and define it in the configuration options. And we create a dataset object that is the object we use to access the data. At the end of this cell, we print the dataset. So if you run this cell, you will see that this print produces a short report of the data stored in the dataset. Here we can see that we have a file with 4 different, as you probably know, The netcdf files have three kind of items inside: the dimensions, the variables, and the attributes. Here we have a file with 4 different dimensions: depth, latitude, longitude, and time, with different elements in each dimension: 32 depths and, for example, 145 latitudes. Here we have short information of the numerical values of each dimension. As you can see, for example, for time, we have time values from 1992 January up to 2018 December. Here we have the list of variables. As you probably know, the netcdf files can have a list of variables with different variables, but here we don't just have just one variable, that is theta O, which is the temperature variable. And after that, we have the list of attributes, or the main attributes of the file, which have some general information of the file. Well, we have opened the file with xarray, and then we jump to the next cell. This is an important one. It's a cell devoted to select the data we want to plot. Here we create a kind of shortcut to the selected data. With this order, we create a new variable that points to the dataset, the variable var name stored in the dataset, and with this function, so we select specific limits for every dimension. So with this first order, we are selecting the data of the variable var name, selecting just the data with depth equals to 0. For this, we use the method called nearest that looks for the nearest values to depth 0. Not necessarily depth is equal to 0. And then we modify our variable, defined variable, by selecting the other dimensions. For example, the latitude, the longitude, and time. For these 3 dimensions, we are not selecting a specific value. We select a range of values. To do that, we use the function slice, and the latitude is defined. We select the latitude as the slice between the lat minimum, lat maximum. That values are being defined in the configuration options. So with this, we are selecting the window we want to plot and the range of dates between initial date and end date. At the end of this line, we print the variable var. We can run this cell, and with this print, we obtain again a short report of the data selected. As you can see in the initial file, we had 145 latitudes, 181 elements of longitude, but in the selected data we just have 109 latitudes and 133 elements of longitude. Same for time, that here we have just 17 elements selected from the 324 elements in the original file. Well, once we have the variable with the selection of data we want to plot, we can jump to the cell devoted to plot the maps. It's, as you can see, quite long because it has to specify many parameters for the map. In this cell, you can see we have a for loop. For every time value in the variable var, we create a time step, and then we format this time step to create a string date. We print this string date, and then we create another variable. Is the data to plot, a specific data to plot. So In this variable, we store the specific data from variable in the specific time step we want to plot in this iteration of the loop. And from here, we start to do the things to plot a map. First of all, to plot a map, we use a matplotlib library, very famous in Python, to create a figure. First of all, we have to create the figure, create the axis, and using the function base map in Python 3, we create an object which is the map with several parameters that has to be defined for plotting maps. For example, the projection, which is in this case a Mercator projection, and for example the limits, the boundaries of the window we want to plot. These limits has been defined in the configuration cell. After this, we start to format several parameters of the figure. For example, we want to draw coastlines in the map. We want to draw the country lines, the boundaries of the countries. We want to fill continents with specific colors. With this, we are creating a land mask. And we want to draw some parallels and draw some meridians in our figure. Particularly, we are drawing 5 parallels between lat max and lat min, and 5 meridians between lon max and lon min. After that, we continue with the formatting of the figure. We have the label of the y-axis, the label of the x-axis, and here we start to work with the data to plot. This part is important because first of all we have to create a grid of lat-long data. In the variable var, the values of longitude and latitude are stored as vectors, as you can see here, for example. Values of latitude just have one dimension from 27, is a sequence from 27 up to 36, and longitude from -18 to -7. But we don't need this, we need a 2D array with the same size than the values we want to plot. For example, the values we want to plot, I think they appear here. We need an array with a size of 109 and a second dimension with a size of 133. So that we use this function mesgrid from NumPy, which is a function that converts these one dimension values in two arrays with 2 dimensions, creating the longitude and latitude grid of data. After that, we have to project these values of longitude and latitude over the x-y axis of the figure. To do that, we use the object map with this order. So we create the values of x and y. The grid, with this we are creating the grid in format XY for the figure, and we plot to plot the data. We use the function pcolorMesh from matplotlib, and we have to pass to this function the variables x, the values in x, the y. This is the grid, the specifications of every point in the grid, and the values of z, which are going to be the colors. These z values are the values of the data to plot variable defined here with the specific time step extracted from the variable var. After that, we specify some parameters in the map, like the color map, the type of color map, minimum value and maximum value. and few lines of formatting of the figure. We are adding a color bar in the figure, and we are adding a label in the color bar. And also we include a title in the figure. This title has been formatted as this string, as you probably know. This is the order to format the strings in Python 3. Just to say that in this order, these brackets will be replaced with the values in these variables. So the title of the figure will be EBF reanalysis, and this bracket will be replaced with the variable name, the value of the variable name, and this second bracket will be replaced with the string date. Here, this is an order to show the figure in the console, and here we save the figure with a name formatted as before with this line, with this command. Here you can see the first bracket is replaced with the path out variable that was defined in the configuration options. And this path out variable was this path, and we use the string date variable to create a specific name for every figure. With this we finish the loop and we start a new iteration of the loop. Well, we can run this cell once it is explained, and here it is. We start to obtain a map of sea surface temperature for every time step in the data set, in the variable selected. Here you can see how the files are starting to appear, because at the end of the loop we are saving the figures. Here, looking at the maps, you can see, for example, we have a map for every time step, since the time set has monthly data in a monthly basis. We have a map for every month. So we have monthly means from 2015 July, August, September, October, November, December, etc. Looking to the results, we clearly see the upwelling processes, which is the signal of cool water near to the African coast that evolves along the year, but as you can see, in summer months, the signal of this cooling is much representative than in winter months, that despite it appears, for example here, you can see there is a cooling of the coastal waters, the signal of the upwelling is always lower. And once the summer starts again, we start to see a clear signal of cool water here in July and August. We also can see the evolving of filaments in the upwelling. The formation of filaments is a very well documented feature of upwelling processes, and particularly this filament developed in front of the Cape Gear and Cape Buscador in the African coast is very well known and well documented in literature. Here again we can see the development of another filament here. Well, once we're here, we have stored all the figures that, as you can see, for example, for the last figure, 2016 November, we can open this figure and it's exactly the same figure. We can download these figures and use it for whatever. Well, once we have these results, we can have the discussion of results. We have seen the behavior of the upwelling. How can we detect the upwelling? We have talking about this by the cooling signal near the coast. Is it stronger in summer or winter? We have said that it's clearly stronger in summer, the signal, and we have already seen the filaments. Here I propose two small exercises. I won't spend time on these exercises in this tutorial, but I encourage you to try these exercises. You have to modify the previous code to show maps focus in specific regions, or you can try to modify the previous cells to plot just one map of a specific date. And these exercises are pretty simple. You just have to change or to modify the configuration options of the program here. Here you can define a different window to plot, or you can define a different range of dates to plot. Well, we can continue with the tutorial with the second exercise, which is the third section of this tutorial. This is the visualization of the upwelling in daily basis with IBI near real-time products. This section is pretty similar to the previous one, but now we are producing maps in daily basis from another different system, IBI system. Here is, as before, the dataset definition. You have the specifications. You have the specifications of you need to download this data from the Copernicus catalog. However, as before, you don't need to download to do this exercise. We encourage you to try it, but you don't need to do it because in the directory data we have the requested data set. Here is the temperature analysis daily NC. That's another netcdf file. In the input section, as before, we have a first cell code with the configuration options with some parameters to be defined. In this case, the parameters defined are exactly the same. We have changed the file name. Now the file name, we are selecting the temperature analysis file in a daily basis. Here is this one. The variable name is exactly the same than before. The boundaries of the window to plot are exactly the same. Here we are changing the record, the times, the initial and final times to be plotted. Here we are defining dates from 1st July in 2020 up to the end of July. We also define the path out where the results will be stored as before. This path is stored. This path is in the folder results, and it is the IBI near real-time daily. Well, we run this code. We pushing the round bottom, and we can jump into the next cell that is pretty similar to the previous one. We open the file name, and we create a dataset object, and we print this dataset to obtain a short report of the data. And here I have included a short description of results. That's a comparator summary with the one obtained with IBI real-time reanalysis data. Do you see any difference? To do this comparison, we can, for example, reduce this, and we can create another view. We can split our window, new view for notebook. And with this, we are splitting our window, and here we have the same page we have been looking in this tutorial. Here it is the report we have obtained for for the reanalysis product. And here we have the report we have obtained for the analysis product. As you can see, they have the same dimensions, depth, latitude, longitude, and time, but the number of elements, the amount of elements in each dimension is not the same. Latitudes, the amount of latitude elements in the analysis products is much higher than in the case of the reanalysis product. Looking to the time variables, you can see they are also different. We have selected, in the case of the analysis product, dates from the 1st July 2020 up to the end of July 2020. And in the case of the reanalysis, we have a longer time record from 1982, January 1982, up to 2018 December. Actually, there is another difference. Here we have daily data in a daily basis, and here in the reanalysis product we have data on a monthly basis. Well, these are the differences, some differences also in attributes, not very important. And in variables, actually, there is no much differences. The dimensions are exactly the same, and the name of the variable is exactly the same. Well, we can continue with this. Once we have uploaded, we have opened the data set, we can jump into the section to select the data to plot. As before, we create a variable from the dataset, a variable var name, stored in dataset. We use the cell function to select specific values of the different dimensions. For the dimension depth, we select the depth equals to 0, or the nearest depth to 0, the value of 0. And we modify the var but with the cell function, selecting the slice of latitudes and a slice of longitudes and a slice of times, defined with these parameters that are defined in the configuration cell of this program. Well, we run this and we will have a fast report, a short report of this variable var. Nothing to say here. As you can see, we have selected 325 latitudes and 397 longitudes. And we can jump to the section where we plot the maps. It's pretty similar. It's a reflection of the code shown before. In the previous case, you can see we have the same for loop for every time value in the variable var. We create a time step, a variable time step, and we format this time step variable as a string, and we create a variable data to plot that is a selection of the data inside variable with this specific time step, which is the time step we are plotting on this iteration of the loop. And after that, we use matplotlib library to create a map with creating the figure, creating the axis, creating the map object with the limits of latitude and the boundaries of latitude and longitude. We format the map as before, drawing coastlines, drawing countries, filling continents, drawing parallels, drawing meridians, the labels in the axis, X and Y. And we create the grid exactly as before by using the msgrid function from NumPy. Here we use the values of the variable in longitude and the latitude in variable, stored in variable, selected variable, and we create two arrays with 2 dimensions in longitude and latitude, and we translate this data of longitude, latitude into the x, y values of the figure with the map object. And to finish, we use the function again, the same function, to plot the color mesh from matplotlib that we have to pass the following information, the x values in a 2D array, y values in a 2D array, and the z values in a 2D array with the same size than the arrays before. And these values are the values stored in data to plot. Data to plot, which is the variable we create at the beginning of the loop, of the iteration of this loop. With this, we are plotting the data, and we add a color bar in the figure, the label of the color bar. We add a title with formatting a text. We add a title with this command, and we format the title as with this command. With this command, we show the figure in the console, and with this, we are saving the figure in the corresponding path out, formatting with this format. With this format, we create the name of the figure. Formatted text, we create the name of the figure using the path out and the string date variables, and we save the figure. Well, we can run again this cell, and again we start to obtain a sequence of the maps of daily data. As you can see in the dates in the title of the figures, we have daily data from 2020, July 1st, 2nd, 3rd, etc. And here in the file browser, we can see how are appearing the files stored. One file for every figure created. Well, looking at the figures, we can see clearly the upwelling processes again. However, as you would probably will see, there is a lot more structure here. The formation, the evolution of filaments are clearer than before. And the evolution of the filament here. And the evolution of the upwelling in other latitudes than Cape Fear and Cape Heather. Rises and decreases with time. Here we have again the list of figures created. These are just the same figures we have seen in the console, but in format JPG. And let's go to the discussion of results. See the influences of spatial resolution comparing the maps obtained with the maps created in section 2. Well, to do that, we are going to split the window as before. Well, here observe the difference of pixel size respect the previous example. Here, for example, we have the results for the previous example with the IBI reanalysis in July, for example. This is year 2020, this is year 2015, but this is the same month. Here you have the differences. We can see clearly the difference in pixel size is clear in these areas with high gradients. With high gradients, it's pretty clear that the resolution of this product is higher, much higher than the resolution of the reanalysis product. Observe also the differences in oceanographic features shown. You can see it's clear that there is more structure in this figure, in this image. This is not only due to the difference in resolution, this is also due because this is a monthly mean and this is only a daily mean. So this is a mean of 30 elements, 31 elements, and this is just the mean. Time daily map. Here we have two questions. Do you think it's possible to plot the upwelling with the same time coverage and frequency than in section 2? Monthly means from 2015 to 2016, but using IBI near real-time data? The answer is not. It's not possible. This is because the near real-time data doesn't have a very long time record, so the near real-time data only has data of the last 2 years stored, so you cannot access right now, to the data of 2015, for example. And another question, do you think it's possible to plot the upwelling with the same time coverage? Excuse me. Do you think it's possible to plot the upwelling with the same time coverage and frequency? Daily means from 2020 July 1st to 2020 July 31 by using the system of section 2. Example, IBI reanalysis. Well, this is not possible. Again, the answer is not. Because the reanalysis system is not updated, is updated in a delay mode. So right now it's not possible to access the data of 2020, for example. It will be updated in the near future, and we will include data of 2020, but right now there is not data of reanalysis data for 2020 in July, for example. However, in this question there is something that the answer is yes. The frequency, can we use the temporal frequency, the daily temporal frequency, using IBI physical reanalysis? The answer is yes. The IBI physical reanalysis, in this example, in this training, we are using the IBI physical reanalysis in monthly means, but you can access the daily means of the physical reanalysis in the CMEMS catalog. Well, here I give you two small exercises, similar to the previous ones, very easy, so you can play with the code before, trying to modify the code and obtaining different results to see how it works. With this, we can jump to the next section, the creation of time series of sea surface temperature. Here in this exercise, we are going to create sea surface temperature time series. In this section, we have an input. We have not defined it. We have not defined the dataset we are going to use, because we are using the same datasets we are used in the previous examples, exercises. So we jump directly into the input section. We have the first configuration cell, configuration options, the first cell with the configuration options, some variables that we will need, some parameters that we will need to run the program. As before, we create a file name. As you can see, this exercise is set to use the temperature reanalysis in monthly basis. The variable name is, as before, the same, the theta O. we have to define just a point in a lat long point. So to plot time series, so we define a specific latitude and just one specific longitude, and we define also the path where the result will be stored. Since we are only plotting just one figure, we will store this figure directly in the directory results. We run this cell code with a triangle, and then we jump to a cell which is quite different than before. We have just a first line to open the data set we are using, but here we are creating a fast map to show the location of the point we are selecting with this latitude and longitude definition. For example, we run this cell, and first of all we obtain the report of the data opened, and we create a fast map with a red dot in the point we are requested. Well, we can jump into the next thought, where it's pretty similar to the previous ones. We are very familiar with these commands now, which is the selection of data to plot. With this, we are creating a variable where we are storing the values and the variable var name stored in dataset, and we use the select function to select specific dimensions. In this case, we are selecting specific values for each dimension. The 0 for this value, latitude, selected latitude and selected longitude, and finally we print a short summary of this variable created. We run the cell. Okay, and from here we can jump into the plotting section. It's shorter than before because we are not plotting a map, we are just plotting a simple figure. We use again matplotlib library, so we create a figure, the axis, and we use the function plot from matplotlib to create a plot, scatter plot. This is of the sequence of values in x and y. In x we are putting the values of time values for every time, because we want to create a time series. In y we are using the values of the variable var. Here some formatting of the figure, including dates in the x-axis, the labels of the axis. We include a grid in the figure, the legend of the figure that is in the lower left corner. We create a title by formatting a text and insert the title in the figure with this command. We show the figure in the console, and we save the figure with this name fig out, which is a string formatted with this command. Well, we can run this, and with this we obtain the figure, the time series of sea surface temperature in the latitude 31 and longitude -11. Here we have a time series where we can clearly see this time series is in a monthly basis from 1992 up to the 2019, and we can clearly see the variability of the sea surface temperature along the year, with a maximum in summer and a minimum in winter. Going to the discussion of results, we can observe and discuss the annual cycle of SST in the selected location. It's already done. What are the real values of latitude and longitude of the time series plotted? Well, we can see these real values Here, when we print the variable, for example, here in the definition of coordinates, we can see the latitude is 31 and longitude is -11. But these values, imagine that we would use something more specific. But here in the configuration of the program, we would be more specific. For example, instead of using 31 and -11, we would use 31.2 and -11.7 or 0.6. We can run this again. We can run and run. Okay, and run this. Here you will see that the selected latitude and longitude are not exactly the same that what we have requested. We have a specific latitude and a specific longitude different than the ones we have requested. This is because we are using the method nearest in this selection process. So we are looking for the nearest points to the requested latitudes and longitude values, right? So if we continue with the program, with the plotting, you will see that the latitude and longitude expressed in the title is not the same that we have, the one we have requested, right? Well, we can remove these changes here. Jump here, run this, and we run this. In this case, we have requested these values of latitude and longitude that, unfortunately, the system can find a grid point just in the requested latitude and longitude. So we obtain the same latitudes and longitudes, but we are looking. Actually, we are looking for the nearest point to that point, right? We are not doing an interpolation with this. We run this, and we create again the time series. Well, alternatively, this is a time series of temperature, but since this doesn't have much relationship with the upwelling processes, because the upwelling is defined, it's more the signal of the upwelling is more clear, not because the temperature of the water that has an annual variability. It's the intensity of the upwelling is defined as the difference of the temperature between the coast and the open ocean. So in the EBMFC, we have a temperature-based upwelling index that is routinely computed and distributed. This is one of our products called Ocean Monitoring Indicators. And it's an indicator of the activity of the upwelling in the last decades and in the last months. In this product, we mix information from the near real-time products and the multi-year products, and we create routinely create figures like this, where we show the coastal upwelling index between latitudes 26 degrees up to 42 degrees north. So we are covering all the northwest African coast and also the west coast, the western coast of the Iberian Peninsula. And we are monitoring the activity of the upwelling in the northern African coast and in the western Iberian Peninsula. We also, this product we provide a trend analysis of the upwelling index computed from the reanalysis product and for every latitude, right? With this, we can jump to the last exercise of this training video, which is the plotting of vertical sections of temperature. As before, we are using a dataset that is already downloaded. It's a dataset that has been previously seen in this video, which is a reanalysis on multi-basis of temperature. And in this, so we don't define the dataset again because it's already done in the first exercise, the second section. In section 2, has been defined in section 2. And here we have the first cell where we define the configuration options with some parameters. In this case, we are defining the file name, the variable name, as in other cases, the initial date and the end date for the sequence of figures, a pass out, which is the results, and IBI vertical sections. IBI vertical sections is this directory, and since we want to plot zonal sections, we have to define a specific latitude, but a range of longitudes between -15 up to -9.5 degrees of longitude. Well, we can run this cell now. And in this cell here, we do the same than in the previous case. In the plotting of time series, we are opening the dataset. We print a report of the dataset, but we are also plotting a fast map where we are including a line with the indicating where is the section selected. We can run this cell. Here is the map, and this red dotted line indicates where we have selected to plot our section, right? In this cell is very familiar to us now. This is a selection of data to plot. We select from dataset a variable var name. We select a specific latitude with using the method nearest as before. And from variable we select a specific range of longitudes and times, defined as a slice between selected section location, section longitude, and the slice initial date and end date. These variables have been defined in the configuration options here, section longitude, section latitude. And we run this cell, so we have a short report of the variable selected. And finally, we plot the figure with this code. Since we have different time steps, selected a different slice of time steps, we have again a for loop for every time step started in the variable var. We create a time step element that has to be formatted as a string, and we select the specific data inside the variable that correspond to that time step. And then we plot a figure using matplotlib. We use the contour f function from matplotlib. Using these x, y, and z elements. In x we use the data to plot values of longitude. In y we use data to plot values of depth. In set values, the colors will be the values stored in the variable data to plot. We use a function to plot contour lines, shaded contour lines, we invert the axis because the depth is positive, but the axis should be negative. In the axis should be negative. We include a grid in the figure, we include a color bar, the level of the color bar, the level of X and Y axis, the title of the figure, we include the title, and we show the figure and we save the figure. Go ahead. Here it is, the section we have created. You can see clearly the tank of warm water in surface warm water here that is pushed towards the open ocean by the wind. So the intermediate waters ascends clear near to the coast, producing this slope in isotherms here. This is, as before, in multi-basis, 2015, July, August, September, October, November, but when the winter starts, fall and winter starts, the gradients of temperature are weaker, but still we can see the inclination of isotherms here, indicating that the upwelling activity is still present. In winter and again in summer appears the strong gradients of temperature between the surface and intermediate waters and between the open ocean and the ocean near to the coast. Well, as the discussion of results, we have to observe and discuss the vertical structure of temperature and compare the result with inshore and offshore. Well, it's already done and discussed it, and we have to discuss the annual cycle of temperature. It's also done. As exercise, here it is a hard one, a hard exercise. You have to modify the previous code to show the meridional sections. So the objective here is not to plot zonal sections like this along a constant value of latitude, but the objective is to plot meridional sections along a constant value of longitude, right? So you will have to change many things in this code. You will, as I said, it's not very easy. You will have to change this. For example, in the configuration options, you are not selecting just one latitude. In this case, you are selecting a range of latitudes, and you are not selecting a range of longitudes. You need to select a specific longitude for the section. You will need to change also, for example, things like this, where we are plotting the line in the map, in this map. Things like this. With this, we are creating a list of elements x, y to plot a line between 2 points. Here you will have to change things because we are selecting in longitude a slice of elements, but in latitude we are selecting a specific element. You have to change this. You have to select a specific longitude value, a slice of latitudes, and here you will have to change also things like, for example, here the x, y. In the x-axis here we are plotting the longitude values, but here to plot these kind of sections, not zonal sections and meridional sections, you will have to change this, including latitude values, right? So in the x-axis you will have latitudes. Well, this is all. Thanks for watching. I hope you enjoyed this tutorial. I'll see you in the next video.